We're now going to get more and more practical with this because we're going to start thinking progressively more about what molecules do when they interact with light. So we're going to talk about what we call vibrational spectroscopy next, which is simply the interaction of molecules with light, considering vibrations specifically, so using our simple harmonic oscillator model. And so the first thing is that we got to remember that the energy of a photon is given by Planck's constant times the frequency, E equals h nu, which you can write as E equals hc times the wave numbers. So we divide by hc and we get the value in wave numbers. The energy of a photon divided by hc is this characteristic number in wave numbers. And remember, we tend to use that as our energy unit. The next thing is that we have to have a quantum transition, what you might think of as a quantum leap here. And that is that the molecule is going to go from one quantum state, one energy state, to another energy state. The Schrödinger equation, the eigenvalues of energy are appropriate here because when we absorb or emit photons, we're changing the energy. And so that's why we fundamentally are thinking in terms of energy here. So we're going to have an initial quantum state, which will indicate with a small I, going to a final quantum state, which we're going to tend to indicate with a small f for initial and final. Now, if the molecule is absorbing light, then a photon with some wave number nu twiddle is going to vanish. It's going to disappear. It's going to be absorbed. And that photon had energy, so the energy of the molecule must go up. If the energy goes up, then the energy of the final state has to be greater than the energy of the initial state. The difference in the energy, however, delta E, is the energy of the final state minus the energy of the initial state. And then we're interested in dividing by hc to get the frequency nu twiddle of that photon there. On the other hand, if we're emitting light, if the molecule spits out a photon, then because we're going to spit out a photon, the energy of the molecule has to go down. So the initial energy is going to be greater than the final energy, and the delta energy is going to be E initial minus E final over hc. Again, that's the frequency of the photon. So the critical thing here is that in spectroscopy, when we emit or absorb light, we care about the energy difference between two quantum states, delta E. So we're going to focus on the energy difference now that we have these energy level expressions. Okay, energy difference. The energy of a photon that's emitted or absorbed is equal to the energy difference in the molecule between the initial and final states. And it depends if it's absorbed, then the final state's higher in energy. If the photon is emitted, then the final state is lower in energy. But that delta, the difference between those two states, is exactly the energy of the photon. The next thing is that those initial and final states, in many cases, can't be just any old value. So the initial and the final states are constrained by some sort of rule, basically. And we call this a selection rule. So we select the values of the initial and final states. And actually, technically, there's this operator called a transition dipole moment. And that's actually indicated with a mu and a little hat over the top because it's an operator. And technically, the probability of going from the initial to the final state is one of these Brocket intervals. So we take the initial state wave function complex conjugate, and then we let the transition dipole moment operator chew on the final state. And what emerges from that is a transition probability. But we're not going to do that in this class. You ought to know that the thing exists. The fact that we call it a dipole moment should indicate that this has got something to do with moving charge around. And we will occasionally point out where moving charge around is relevant here. Because if you think back to physics 2, you'll remember that what's going on in an antenna, which is absorbing or emitting photons as well, that's radio waves. What an antenna is doing is basically taking a charge and waving it around in space. So when charges move in space, when charges accelerate, there tends to be emission or absorption of photons. And so basically the molecule's acting like an antenna, and so the difference in the initial and final states needs to have moved some charge in some way, and we call this thing a transition dipole moment. Now all we're going to do in this class is talk about the rules that we have. So just we'll state these things that we call selection rules. So first of all, for absorption, it's pretty darn simple. For a simple harmonic oscillator, for absorption to happen, the vibrational quantum number goes up by 1. Not anything, just 1. And it's exactly and precisely 1 if it's truly harmonic. Now, as we'll see very shortly, molecules aren't truly harmonic. And so you can have a delta V of 2, 3, etc., and we call these overtones. But they're much, 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 much less weaker. So in the context of this course, we'll focus almost entirely on this very simple rule that the vibrational quantum number, if you absorb a photon, remember, energy's got to go up, so the quantum number's got to go up, and that's just a change of 1. The next part of the deal is the molecule actually has to be in the initial vibrational state. So VI has to be what we call populated. And if you'll remember, we were talking about the characteristic energies of vibrations earlier, and for most vibrations of molecules under room conditions at least are almost always in the vibrational ground state. So really, mostly, the initial vibrational quantum number is basically 0. Now, there are, again, spectra with the initial vibrational quantum number of 1, 2, etc., and those tend to be called hot bands because they become more prominent as the temperature goes up. Because as temperature rises, then there becomes the energy in the bath is enough to excite some molecules just via thermal excitation into vibrationally excited states. So we've got overtones if the quantum number jump is too high. We've got hot bands if the initial vibrational quantum number is basically too high. But for almost everything we're dealing with here, we're going to have an initial vibrational quantum number of 1, and we're going to just go up 1 vibrational quantum number. Now, spectroscopists have this thing they call a term, and so we talk in terms of the vibrational term, and that's given capital G, and it's just G of a vibrational quantum number, V plus a half, is equal to V plus a half times the characteristic frequency nu sub e, or the equilibrium frequency of the molecule. So that's just our simple harmonic oscillator vibrational energy level ladder here. The characteristic frequency is 1 over 2 times pi times the speed of light times the second derivative, the square root of the second derivative of the potential energy divided by the reduced mass, and that in turn is equal to our favorite number, 5.8074, times the square root of the second derivative of the potential divided by the reduced mass, if we want the energies in wave number units. The distance is in angstrom, and the reduced mass is in atomic mass units. So using the characteristic atomic units, we get our favorite 5.8074 and the formula we're already used to there. So the energy difference then is known as delta G, and that's just G of V plus 1 plus a half, so that's the final state, minus G of V plus a half, that's the initial state. And that's just characteristic nu E. So that's pretty easy. One thing to point out here is that second derivative there we're looking at. That is the second derivative at the bottom of the well, and we'll look at that a little more. So that's actually why we use the equilibrium value here. But this is, right now, is for the simple harmonic oscillator, where the second derivative is a constant. So the important thing there is that the frequency of the light absorbed is just that nu E. So the photon that's absorbed has the same frequency as the characteristic frequency of the vibration. And so that is determined, that's characteristic of a given molecule. And clearly my writing's getting a little slanty today, but such is life. So it's characteristic of a given molecule. And that characteristic is because of that term, the portion of the expression there that's given by the second derivative of the potential, which changes somewhat from molecule to molecule, and then also the reduced mass of that bond, which changes enormously, is very, very dependent on what the atoms are that comprise the reduced mass. So that's why we can use that vibrational absorption to learn these it's really tying us into the reduced mass of the vibration and also that bond strength there, the stiffness of that bond. So another thing to note is that, speaking of strength and stiffnesses of bonds, a characteristic bond strength for a single bond is about 30,000 wave numbers. And we compare this to a typical equilibrium bond energy of about 1,000 wave numbers. So let's start to look at what a bond might actually look like. So let's start to move a little bit away from the simple harmonic oscillator. So we'll draw some axes here. I've got a bond distance RAB in angstrom. I've got an energy in wave numbers, and an actual potential energy that associated with a bond that might be vibrating for a diatomic system looks something like this purple curve here. And there will be a point of a minimum, and we call that the equilibrium bond distance. So we use sub E always to indicate the bottom of that potential there, the bottom of that parabola, the bottom of that well, as we often call it. And that's typically somewhere between 1 and 1.5 angstroms. For a few systems, the bond can be a little bit less than an angstrom. But basically maybe 0.7 to 1.5 angstroms is the absolute range of bond lengths that you might ever see. 1.5 is a really long bond as well. Other elements of this that we care about, so this distance from the bottom to the broken bond is typically 30,000 wave numbers or so for a single bond. We're going to have some vibrational energy levels in there, and I've actually spread them out a little bit just for the sake of space. But there will be the ground state V equals 0, the first excited state V equals 1, and then a whole ladder going on in there. Now that separation is typically 1,000 wave numbers or so. So actually drawn to scale, I could fit about 30 of those into this entire system, as we'll see in a bit. And now also, let's carry that out a little. The typical characteristic 0-point energy, if I have 1,000 wave numbers, remember the 0-point energy is a half that characteristic frequency. So the 0-point energy is going to be maybe 500 wave numbers or so out of 30,000, which isn't very big, but it's also not nothing. It's enough that we care about. It's more than KT. It's more than the characteristic 200 or so wave numbers that you get just from thermal excitation. So 0-point energies and things that make it change especially are actually things that we care about. Now we can extend this bond asymptote in there a little bit so we get some more space, and note that the actual bond strength here is equal, D naught is equal to the equilibrium bond strength, dE, minus the energy of the lowest energy state that we can cram into this confined space. So the actual equilibrium bond energy is equal, D naught is equal to the dE minus the 0-point energy. And again, that 50, the molecules that have many, many vibrations can have many thousands of wave numbers of 0-point energy. But for a single breaking bond, we're typically going to have 500 if it's a stronger CH stretch at 3,000 wave numbers, it's got 1,500 wave numbers of 0-point energy. So it really does matter. And we'll see many cases where that's true. So D naught, which is the actual bond dissociation enthalpy at 0 degrees Kelvin, so that's an actual chemical quantity we care about. D naught is equal to the absolute depth of the well, dE, minus the lowest energy you can possibly get, which is the 0-point energy. Now this curve actually looks a lot like a function that we call the Morse potential, or the Morse oscillator. And the Morse function is actually a really nice function to work with, so we are going to use it in this class. And here's the functional form. It's equal to that dE times a term that's kind of an exponential. It goes like 1 minus exponential of a minus times a characteristic distance a times r minus re, how far away we are from the equilibrium distance. That whole thing, 1 minus exponential of negative a times r minus re, the whole thing squared. Let's see, note a couple of things about this. First of all, that value a is equal to 1.58074 times the square root of the reduced mass times the equilibrium frequency in wave number squared, divided by twice the equilibrium bond dissociation energy. That's kind of a bizarre number, but that's how it works out. That's what the number is. Here's our friend again, 5.8074. I hope you get to see that that comes around a lot. And once again, this is given the units here on the y-axis over there are in wave numbers. So the bond dissociation energy is in wave numbers, the potential is in wave numbers, the distance A is in angstroms, and the reduced mass is in atomic mass units, AMU. So we've got molecular units, AMU, angstrom, wave numbers for energy. Now note from the function there, if R equals RE, then that term in the exponential is 0. E to the 0 is 1. And we get 1 minus 1, and the value is 0. So that's the bottom of the well there that we have at RE over with the red tick on the left axis. If R is really, really big, then I have an e to the minus some big number, right? If I have e to the minus some big number, then that is 0. So then the potential V just goes to dE. Well, that's good. That has the right asymptotic value there. So we get the 0 at the equilibrium bond energy. We get the dE when it's really, really big. The exponential becomes, something not in between really, really big and nothing at that characteristic distance A. Actually, it's 1 over angstroms is the unit of A, and that is typically, again, some tenths of an angstrom. So that's not too terribly different from the half width of the Gaussian that we were looking at earlier. The distance from from classical turning point to classical turning point. Now, if R is, let's say, 0, then the Morse function has some finite value, which actually is not quite physical. But since A, as I said, is typically maybe something like a tenth of an angstrom or so, and RE is maybe 10 tenths of an angstrom, 10 times A or more, e to the 10 is an enormous number. And so the potential, as you make the distance really small, gets enormous. It gets absolutely huge. So the potential basically goes to something that's more or less infinity as the bond gets squished too far. And we'll talk more about why that happens later in the class.